Okay, hello everyone. I hope you are doing well. This is actually exam 2 midterm for fall 2025. So I just want to go through all the questions and solve it together. I will also provide some shortcuts that, in particular for multiple choice question, that might ease your life. So let's get it started. The first question is you are given a matrix. You're supposed to find the rank of A and nullity of A, and then compute A plus 2 nullity of A. So we can easily just do the echelon form of this matrix. So I will make 0. So I basically multiply the row 1 by -2 and then add it to the second row. So therefore it's going to be 0. Therefore, and then this going to be 0. Right, and then if you multiply by -2, and this going to be +1, and then now I multiply row 1 by -6 and then add it to the third row. So therefore it's going to be 0. This is going to be 0. This is going to be 0. And then this is going to be -6 by -1, 6. And then here I have +4. So, and then I can also multiply row 2 by -4 and then add it to the third row, and then therefore I can make this one 0. Therefore, as you see, the dimension of row space is equal to 2, which is equal to dimension of column space, which is equal to rank of A. Therefore, rank of A is equal to 2, and then we know that rank of A plus nullity of A is equal to the number of columns, which is equal to 1, 2, 3, 4, 5 columns. Therefore, this is 2. Therefore, nullity has to be 3. So now it remains to compute what? It remains to compute rank of A plus 2 nullity of A, which is equal to 2 plus 2 times 3, which is equal to 2 plus 6, which is equal to 8. Therefore, number 1 is this option, which is pretty nice. And now let's move on and then go to question number 2. So it's one of the typical question related to linear independency or dependency of set of polynomials. So here you are supposed to find the set such that those vectors are linearly dependent. So not independent, dependent. So therefore you should look for one of the sets such that some of the vectors are redundant. What that means, it means that some of the vectors can be produced by the other one. So if you carefully look at all of the options, you will see that on part E, for example, here you have this, and then you have this. So but instead of this, you can easily consider, you can replace t squared because a scalar multiplication doesn't impact on linear independency. And now if you consider this, and then now if you add this and this term, 2 plus 2t minus t squared, then minus 2t squared, which is this term, then what you get is 1 plus t minus t squared, which is exactly the first term. Therefore, as you see, this term, the first term is basically a linear combination of the second and third term. Therefore, E is going to be your solution. So let's move on and then go to the question number 3. So here is a kind of conceptual question. So for conceptual question, my advice is that don't read the statement first. So first go to these options here and see which option is more beneficial to check first. For example, you can easily, by checking this option, you can easily you can easily check whether your how many of your choices can be eliminated. Let's check this option. As you see, the dimension. Okay, what's the question? The question is that find the subspace such that the dimension of this subspace is 4. So let's check whether the dimension of this space is 4 or not. So you have this condition on your variables, so one can easily say that. So okay, this implies that x is equal to z plus s plus t. Now one can see that any x, y, z, s, t, s and t can be written as, okay, instead of x you can just write s plus z plus s plus t, and then write it y, z, s, t. And now you can just factor it, factor z, this can gives you a vector, then factor y, this can gives you a vector, and then factor s, and then factor t, right? For example, if you factor z, so what you have is 1, 0, 1, 0, 1, and then 0 and 0. If you factor y, for example, you have 1, 0, 1, 0, factor y, sorry, you have 0, 1, 0, 1, and then 0, 0, 0, and then for example for s, everywhere is 0 except 1 and here 0, and then for t you have 1 and everywhere else is 0. As you see, this subspace can be generated by these vectors here, these 4 vectors. Those are linearly independent. The dimension is 4. Therefore, this is one of the solution of your question, right? So therefore, you can easily remove this one, remove this one, remove this one. So then you left with E and F. So it doesn't make sense for you to check this third option. Why? Because it is in both cases. So therefore, you can easily, for example, check the first one. So and then find your correct answer. If you check the first one, all polynomials of degree less than or equal to 4. Okay, this basically means that P4, and we know that the dimension of P4 is always is 4 plus 1, which is equal to 5. So just don't forget that this is usually a actually typical mistake that some of the students do. So you should remember that the dimension of Pn is equal to n plus 1. So here the dimension is 5. Therefore, I is not the answer. Therefore, I is not the answer. Therefore, D is the solution. So therefore, as you see, by checking only V and this one and I, you can find your correct answer. So let's move on and then go to the fourth question. So which one of the following statements is always true? So actually, majority of students actually opt for A, but this is not the answer. So let's read this question carefully. A vector x in R4 satisfies ax is equal to 3x. Then x must be an eigenvalue. So most of the students think that this is true, but this statement is not correct, because most of the students think that this is a definition of eigenvalue. But remember that the definition of eigenvalue has x is not equal to 0. So therefore, this statement is definitely not true. Let's move on and check statement in part B. So statement in part B, so you have this eigenvalue for A, and then therefore this is going to be eigenvalue for this. So this is basically coming from the fact that if AV is equal to lambda V for V is not equal to 0 eigenvalue, then if you consider the power of K, for example, AK, V is going to be lambda to the power of KV. So this is actually kind of hints you should always remember. So therefore here we know that 1 minus I is the eigenvalue for this. Therefore the eigenvalue for A2 is going to be 1 minus I squared, which is equal to 1 plus I squared minus 2I So therefore this and this cancel out, and therefore you have negative 2i. Therefore negative 2i is going to be eigenvalue. So we know that sometimes you can write, for example, you can write like this. So is equal to negative because basically this is you can write it like this. So here you can see that then here v or negative v can be is equal to negative 2i and then v. So it's easy. So then you can put the negative I here. Therefore here you have this. So therefore what you prove is that a to minus or opposite of v is equal to 2i and then negative v, right? So you should always remember that any scalar of eigenvectors can be again eigenvalue. Therefore you are fine. Therefore this b is going to be correct solution. You don't have to check the rest of the question, but for the sake of the discussion, I will check a few of them. For example, if you have a matrix whose polynomial is this, therefore a is diagonalizable, which is not correct because here you have eigenvalues are 0 and 1 with multiplicity 2 each of them, but we don't know, maybe the multiplicity maybe the dimension of kernel of for example a minus lambda I cannot reach the multiplicity of each eigenvalue. So therefore this is not the answer. So a has this characteristic function, then a is not invertible. So 0 is one of the eigenvalues. So here, and then if 0 is the eigenvalue of matrix A, then A is not invertible. But here is mentioned that it's invertible. They want you to confuse. Therefore, this is not the solution, and then E also not the solution. Let's move on and then go to question number 5. Question number 5 is a matrix representation of actually a transformation. Remember the order of the basis here is very important. So what you should do, so here we have t from R3 to R3. So here, based on the order of this, you have B1, B2, B3. So you can easily compute t of each of them, t of B1, and then here t of B2, and then here t of B3. So, and then when you compute all of them, so that is already given, you should consider the order of the bases. Here they put in a different order, but for example t of B1 is based on the order B3 and B2 and B1, but what I want is to write based on the order of minus B1, minus 2B2, plus B3. So therefore the first column of my matrix is going to be what? It's going to be -1, -2, and then 1. Now it's time actually to compute the second column. The second column, t of B2 is here, is the -B1, -B1 plus B3. So therefore here I have -B1, 0 for the coefficient of B2, and then 1. And then here t of B3 is gonna be B2 minus, oh sorry, because I have to comply with the order of the basis. Therefore I will write first B1 and then B2, and then 0 B3. So therefore here you have -1, -1, 1, and then 0. So here is a matrix representation corresponding to your matrix transformation. Just remember two things. Order of the basis here is very important. So now you should compute the determinant of t. So and then determinant. So I would say is pretty straightforward because you can easily, for example, add first column to the third column, and then here you can get 0. Here you can get 0, and then here you can get -1. then the determinant is going to be -1 times determinant of this part, and determinant of this part is going to be this time it is -2, and therefore the answer is 2, and therefore I just have choose A. So now let's move on and then go to question number 6. Question number 6 is you are given A and then V, and then you should compute AV, A to the power 10 matrix multiplied to V, and then find A minus B, right? So even if you don't, first of all, this question is one of the interesting applications of eigenvalues and eigenvectors. But even if you don't have any knowledge, I mean, of eigenvalues, I believe you have, but if you don't, so it's easy to compute that, because, for example, you can easily compute A to V. So let's compute it, 4, -3, and 10 to -1, and then this is 3, 2 is equal to what? So this is equal to 12 minus 6, which is 6, and then this time this, which is equal to 6 minus 2 is equal to 4. Therefore here is 4. I can factor 3. Therefore I have here 3 and 2. So therefore, as you see, I have AV is equal to 3V. So, and therefore A to the power 10V is gonna be oh, sorry, here I meant 2. I should factor 2, right? And here A to the power 10V is going to be 2 to the power 10, and then vector V, which is equal to 3, 2. So therefore, this is going to be 3 times 2 to the power 10, and then 2 times 2 to the power 10. So this is equal to AB. So now let's compute A minus B. A minus B is equal to 3 times 2 power 10 minus 2 times to the 2 power 10, which is equal to, okay, let's factor the power 2 to the 10s. Therefore here I have 2 minus 2, which is equal to 1. Therefore the answer is 2 to the power 10, which is equal to C, which is pretty, I think, straightforward. So now let's go to the second question. So here is the question related to application of eigenvalues and eigenvectors to differential equation. So as you see, the complex eigenvalue is already given and the complex eigenvector is already given. Then you are done. So you can easily say that the solution of this system is going to be x of t is equal to v1 e to the lambda 1t. Okay, let's replace. So what is v1 is 2 minus I, and then -1 plus 2i, and then here e to the lambda 1 is 1 plus 3i, and then t. So but this solution is kind of complex solution for this answer. We need to compute the imaginary part and the real part, and then consider the linear combination of imaginary part of the solution, and then imaginary part and real part. For example, you can write this one as e to the t, and then e to the 3ti, and then instead of this, compute cosine of 3t plus I sine of 3t, and then and then you can also decompose this vector to the imaginary part and then real part like this, then -1 and 2, right? Then this is a simple computation to do the rest of the computation, but here is the small hacks here that one can use and then choose the correct answer. You see, if you take t to be 0, therefore this one plus a linear combination of this one is going to be the solution. Therefore, if you take t to be 0 in all of your choices, and then see which one gives you 2 and -1 and -1 and 2. For example, if you look at this option, if you take t to be 0, right? So if you take t to be 0, okay, you can get negative 1 and 2 here, then okay, might be the answer. And then, but here, if you take, for example, t to be 0, you cannot, here you can get 1 and 2, therefore this is not the answer. Here again, you cannot get, because here if t to be 0, here you can get 1 and negative 2, which is not here, therefore this is not going to be the solution. So here you can get negative 1 and 2, which can be solution. Here again, you cannot get negative 1, and therefore this is A is not also solution. Then therefore, now you should choose between B and E, but you didn't check this part. 2 and negative 1 should be solution. 2 and negative 1, okay, 2 and negative 1. If you take t to be 0, here you have 2 and negative 1. So, but here if you take t to be 0, here you have 2 and 1. So, therefore, this is not the solution. Therefore, the correct answer is B. You see, by just taking t to be 0, you can easily find the solution. I hope that this shortcut actually method helps to find the correct answer. So now let's go to the free response question. So here you have a question. You are given a matrix, and then you are asked to compute the eigenvalues and eigenvectors. So to compute the eigenvalues, so just remind you that determinant of A minus lambda I3 is going to be 0. But here, because you have 2 0 here, one can easily see that 3 minus lambda is going to be one of the factors of your characteristic function. It's easy to see that, because here if you multiply negative 2 here, then determinant is going to be this times the determinant of this part is equal to 0. Therefore this factor, if this times this is equal to 0, then this factor can be 0. Therefore one of the eigenvalue, for example lambda 1, is always 3. Now you can use this trick that if you have a 3 by 3 matrix, so the summation of your eigenvalues gives you trace of A. Trace of A means the summation of all the entries on the main diagonal. For example, for this case, trace of A is gonna be 7, but you already have one of them, which is equal to 3. Therefore lambda 2 plus lambda 3 is gonna be 4. And then we know that lambda 1 times lambda 2 lambda 3 is going to be determinant of A. So then here you can compute the determinant of A. Determinant of A is going to be 3 times 4 minus 1, and then just substitute lambda 1 to be 3. Therefore you can cancel this and this. Therefore lambda 2 lambda 3 is also equal to 3. So now by these two equations, you can easily see that lambda 2 is also equal to 3 and lambda 3 is equal to 4. So those are the list of your all eigenvalues. So but the question is asked for eigenspaces as well, basis for eigenspace for each eigenspace. So now to compute the basis for eigenspace is enough to compute kernel or null. So it doesn't matter, those are the same for matrices. Null of A minus lambda I3. So you should compute this one for each eigenvalue. So let's start with, for example, lambda 1 to be 3. So therefore you should compute kernel of which matrix, or okay, if you're concerned, so maybe I can use null, because most of my students, they like to use null rather than kernel. Okay, let's compute null space of A minus 3I3. Okay, you can easily see that this is going to be null space of which? Null space of 0, 0, 0, and then here you have 1, negative 1, and then 1, and then here you have negative 1, 1, and then negative 1. Is that correct? So we have to compute the null space of this matrix. So one can easily see that if you okay, now let's work to find the echelon form of this. So if you want to find the echelon form of this, is easy to actually add row 2 to this second row to the third row, and then you can get 0 here and 0 here and then 0 here. Therefore, what you get is basically just this row. You left with this row. You are left with this row. Therefore, we can encode this. Therefore, here x1 minus x2 plus x3 is equal to 0, and this implies that x2 is equal to x1 plus x3. So now x1, x2, x3 is going to be what? Okay, x1 is x1. Instead of x2, I write x1 plus x3, and instead of x3, I write x3. So we can factor x1. Therefore, you have this vector 1, 1, 0, right, plus x3, and for x3 you can write 0, 1, 1. So okay, so this is basically this gives us the actually the or eigenvalues. So we have two eigenvalues. So this one is this one, and then this one v lambda, and then here v lambda prime, right? So therefore we can say that the eigenspace for lambda is equal to 3 is equal to a span of those vectors 1, 1, 0, right, and then 0, 0, 0, 1, 1, and the basis for that one, the basis for lambda is equal to 3 is just the set of those vectors 1, 1, 0, and then 0, 1, 1. So okay, I'm done with this part. Now let's work on that part that if I take lambda 3, which is equal to 4, and then find the null space of A minus lambda. Okay, therefore I have to find the null space of this matrix here. Null space of A minus 4 lambda. Therefore here I have negative 1, 0, 0, and then here I have 1, here I have negative 2, and then here I have 1. Here I have negative 1, 1, and then negative 2. So here we go, a very nice matrix. So to compute the null space, I can actually add the first row to the second row and make this one 0 easily. And then I can multiply the first row by negative 1 and then add it to the second row. Therefore, I can make this one 0. So, and then actually I can now I can multiply the second row by 2 and then make this one and this one 0, and then what I left is this nice matrix. So if I encode the first one, what I have is x1 is equal to 0, right? If I encode this row, and then if I encode this row, I have negative 2x2 plus x3 is equal to 0, and then therefore this gives me x3 is equal to 2x2. So therefore the eigenspace for the eigen is okay. Therefore here what I have is x1, x2, x3. Let's compute the answer. It's going to be x1 is 0, x2 is 2x2, and then okay, wait. So I think I made mistake somewhere. Let me check my solution. If I check my solution, sorry, here if lambda is equal to 4, therefore here I have negative 1, 0, 0. Sorry, I'm just checking my answer to see whether everything is correct. So negative 2. Oh, I see. Okay, so I think that here, if I want to consider this one, lambda 1 is equal to 1. Sorry, my bad. So here it should be 1. And therefore, when I want to compute this null space here, when I want to compute this null space here, so I should basically compute, okay, sorry about the confusion. So here lambda 3 is equal to 1, so therefore I should compute the null space of A minus I3. So let's compute this one. So I should compute then the null space of which matrix? Should compute the null space of 2, 0, 0, and then here I have 1, 1, 1, and then 1, and then here I have negative 1, negative 1, 1, and then 1. Okay, I should compute the null space of this one here. So I can make this one and this one 0 easily. So then I can multiply this first second row by negative 1 and add it to the third. Therefore, I can make this one 0. Okay, now I think I am all set. So 2x1 is equal to 0. This implies that x1 is equal to 0, and then x2 plus x3 is equal to 0. Therefore, this implies that x2 is equal to negative x3. So now, okay, so therefore my solution is going to be x1, x2, x3. Okay, x1 is 0, x2 is equal to negative x3, and then x2 is x3 is equal to x3. So therefore I can factor x3, and then what I have is 0, then negative 1 and 1. Now we can easily see that the eigenspace for lambda is equal to 1 is equal to a span of this vector 0, negative 1, 1, right? And then the basis for eigenspace corresponding to lambda is equal to 1 is just this set 0, negative 1, and 1. So and now as you see, the dimension of this null space is equal to 1, which is exactly the multiplicity of lambda 3 is equal to 1. And the dimension of this null space is equal to 2, which reach the multiplicity of eigenvalue 3. So therefore, we can definitely diagonalize the matrix, which is actually the second part to diagonalize the matrix. So I should define matrix D. Matrix D is always just put the eigenvalues here, put the eigenvalues. So the order of the eigenvalues doesn't matter, but you should pay attention. For example, if you write 3, 3, 1 here, and then everywhere as 0, here the matrix, the invertible matrix should be, the first two columns should comes from the eigen vectors for 3, which is this one, 1, 1, 0, and then 0, 1, 1, and then the third column should be the eigenvalue, the eigenvector corresponding to 1, which is 0, negative 1, and 1. So therefore, this is your matrix P, this is your matrix D, and then you are done with question number 8. Okay, let's move on and then go to question number 9. Question number 9 is also another application of eigenvalues to differential equations when the eigenvectors are real, in fact. So to do that, so the first, okay, you are given a matrix. So fortunately here you don't have to compute the eigenvectors. The eigenvectors is already given. So, but you have to compute the eigenvalue, which is much easier. So let's compute A V1. If you compute A V1, okay, here you have 0, 1, negative 3, negative 4. V1 is 1, negative 3, which is equal to negative 3, and then here you have negative 3 plus, which is 9, right? Which is equal to, if you factor negative 3, so therefore here you have 1 and 3, so which is basically negative 3v, right? Therefore, so here the eigenvalue v1 is corresponding to lambda 1 is equal to negative 3. And now I have to compute the eigenvector corresponding to this one. Again, you can use this trick that multiplication of lambda 1, lambda 2 is determinant of A, and then summation of lambda 1, lambda 2 is equal to trace of A. So those are, you should always keep in mind, and this is true for general. Multiplication of all the eigenvalues is equal to the determinant of A, and then the trace of A is equal to summation of all the eigenvalues. So for this case, because you already have lambda 1, therefore you can just say that what is the trace of A? Trace of A means the summation of all the entries on the main diagonal, which is equal to -4. -4 is lambda 1 plus lambda 2, but I already have lambda 1, which is equal to -3. Therefore, you can easily see that lambda 2 is equal to -1, or -1, right? So therefore, the eigen value for V2 is lambda 2 is equal to -1, right? So the second part, you're supposed to obtain the general solution. The general solution is going to be x of t is equal to c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. I always recommend in this to write the general formula and then substitute for free response question. So here, therefore, here you have c1. Therefore, here you have c1 e to the -3 t, and then v1. v1 is 1 -3 plus c2 e to the -t, and then the vector, the corresponding eigen value 1 -1. You can a bit clean up this equation. So therefore here you have c1 e to the -3t, and then plus plus c2 e to the -t, and then here you have -3 c1 e to the -3t, and then here plus minus c2 e to the -t, right? So, and therefore this is going to be your x of t and then y of t. So okay, you are done basically with the first part. So for the second part, you should actually compute the x of -1 and y of -1. So x of -1 is already here. Y of t is also here. But the problem is that here, I forgot, by the way, to mention that here C1 and C2 are just real numbers. Don't forget to write this one, right? Because C1 and C2 can vary. So those are real numbers. So now our job is to compute C1 and C2 because I have extra information here. So remember that x of 0, y of 0 is equal from this side you can write 5 and -11. And now if you substitute here t to be 0, what you have is c1 plus c2, and then here -c1 minus c2. So therefore this equation gives you this actually system that c1 plus c2 is equal to 5, and then -3 c1 minus c2 is equal to -11. So now you can easily compute c1 and c2. For example, if you add them up, so you have -2 c1 is equal to -6, therefore c1 is equal to 3. And then if you substitute c1, for example, to here, you will see that c2 is equal to 2. So therefore, here you can easily see that in the general solution, in fact, c1 is equal to 3, right? c1 is 3, c1 is 3, and then c2 is 2. I just write it down here. Now we want to compute what? X of -1 plus y of -1. Okay, x of -1, just plug in -1 here. Therefore, here you have 3e to the, so here I'm plugging t to be -1 here. This is x of t now, and this is y of t. So if you plug in here, therefore here you have 3e to the power t e3 plus 2e to the 1, but I don't write it, then plus y of -1. Y of -1 is gonna be -9e to the 3, and then -2e. So as you see, this and this cancel out, this one and this one cancel out, and then this and this, consider this and this, you can say that -6e to the 3, and this is your final solution. So we are done with question number 9, and let's move on, then go to question number 10, which is the last question. So you are given actually transformation from P2 to 2 by 2 matrices. By this definition, the first one is find all the polynomials such that P of t is equal to 0, and then the second one, determine the basis for the kernel. So to obtain the kernel, so you definitely should use the first part. Therefore, you should be very careful to compute the solution for the first part, and then for the third part, so you have to compute the basis for the range of t, which is not related to part 1 and part 2. It can be separately. So now okay, let's compute the first part. So I want to compute all t of all polynomials such that this and this. So let's t of all polynomials of degree 2, a plus bt plus ct squared is equal to 0, 0, 0, 0. Okay, so what is the rule for this? The rule for this is just p1 and then 0, 0, p2. So based on this equation, what I have is, this means that p1 is equal to p2 is equal to 0. Therefore, this implies that p1 is equal to 0. Okay, what is p1? It means that substitute t to be 1 here. So therefore, a plus b plus c is equal to 0. And then p2 is also 0. This means that just substitute t to be 0 here. Therefore, a plus 2b plus 4c is also equal to 0. I can subtract those equations and then get b plus 3c is equal to 0. Therefore, this implies that b is equal to -3c. This is one relation. And then the second relation is that I can substitute this one to first one and then say a plus b plus c is equal to 0. Okay, substitute b to be -3, -3c. Therefore, a is equal to 2c, right? This is all the equations that I need. Now, the final answer is that you are basically, okay, here you should write the coefficient of your polynomial by considering those relations that you already compute. Therefore, a is equal to 2c. Therefore, 2c plus b. What is b? b is -3c t plus c t squared. So this is basically your p of t here, and then you can also factor c. So, and then here, therefore, you have 2 minus 3t, and then here t to the cube. Therefore, because you want to find all the polynomials such that t of p is equal to 0, and then I already compute all of them, therefore the answer is a span of 2 minus 3t plus t squared gives you all the polynomials such that t of these polynomials is equal to 0. For example, you can also easily check your answer. If you check the t of this, t of t minus 3t plus t squared is equal to what? Is equal to p of 1 and 0, 0 and p of 2. And then if you compute p of 1, you can easily see that this is going to be 0 here. And then if you compute p of 2, here you have also 0. So you don't have to write this. I just wanted to show you that I just wanted to show you that you can always check your answer. Therefore, this is going to be your answer for part 1. And for the second part, so you need the kernel of your transformation T. So the kernel of T means that the all elements in the domain. What is my domain? Domain is P2. It means that all elements like this, CT squared, such that T of A plus BT plus CT squared is equal to 0 of the codomain. 0 of the codomain is 0 matrix, right? So, and now using the first part, because I already compute what those matrices are from the first part, and this is basically a span of 2 minus 3t plus t squared, right? But here, remember, I need a basis for the kernel. The basis is always a set of vectors. Basis for the kernel of T is basically this set, negative minus 3t plus t squared. So therefore the dimension for kernel of T is equal to 1. You don't have to write the dimension of kernel of T is equal to 1, but I need that one to check my solution at the end of the day. So now let's go for part 4. Part 4, you are asked for to find the basis for the range. So and in fact it's pretty easy and straightforward to compute that, because p of remember that t of any t is going to be what? Is going to be p1 0 0 p2, right? So but you should always remember that this p1 and p2, those are just always numbers. Therefore you can decompose this matrix to two matrices, 0 0 0 0 plus p2, then 1 0 0 0 0 1. So those are linearly independent in 2 by 2. Therefore the range of T is equal to a span of these matrix 1 0 0 0 and also 0 0 0 1. And the basis for the range, of T is basically those two matrices, right? 0 0 0 1. Therefore you can easily see that the dimension for the range of T is equal to 2. So, and there is actually kind of generalized version of rank theorem that dimension of kernel of T plus dimension of range of T is equal to dimension of the domain, which is equal to, here dimension of the domain is P2. Dimension of P2 is equal to 3. So the dimension of kernel 1, dimension of range is 2, and therefore you can see that your answer is correct. So that brings us to the end of this review session for exam 2 for fall 2025. I hope that my comments and this video is or all of them are helpful and beneficial, and I just want to wish you best of luck for your exam. Take care.